Okay, so I've got my frequency data here, and to convert this into something that looks more like a probability density function, I need to divide by the total number. So I'm going to take, first of all, equals the sum of this data down to the bottom value, which was 999, because we capped it off at 1,000, remember? So that's 13,460, and all I need to do now is divide this column here by that, which I will dollar with the F4, and so I can see what my relative frequencies are of each of these values. Now if you notice there, it's only gone down that far because it's seen the space there and thinks it doesn't have to go any further. That's the sort of error that can happen in the real world, and you get the answers wrong, and you end up with insurance companies that crash because they don't have enough money to support the liabilities. So make sure you check things like that in spreadsheets. It's the sort of thing you'll be doing when you start work, so always worth that sort of check. And what I'm going to do now is look at some of these distributions. I'm going to start with a really simple one to illustrate the point, which is the exponential distribution, which you will remember the probability density function is lambda e to the minus lambda x. So I'll just call this column, if I can spell, exponential, and I'll start with a value of lambda of 1. You see, name that cell lambda. So now I'm going to put that formula in here. So it's lambda times exponential e to the power of minus lambda times x. So x is the value here. But remember, that's not quite right, because the 45 frequency here refers to all values between 0 and 1. So my x is in fact not that value there, but that value plus a half of it on average, plus the step value divided by 2. And the other thing you'll notice here is I've got top left in there. Now when I try and drag that down, that's not going to drag down because it's a label, so I'm going to replace that with F7, so that form will then drag down. And you can see this formula falls pretty quickly to close to 0, so it's probably not going to fit very well, but I'll just have a quick look. First few values, see what happens. And you can see the distribution doesn't fit at all well, but that's not to worry. We can change our value lambda to see if we can get it to fit a bit better. But when we look at goodness of fit, we typically look at the root mean square difference. So to break down what the root mean square difference is, first of all, it's looking at the square of the differences. So we're going to look at this value minus this value to the power of 2. Then we're going to look at the square root of the mean of that. So let's do that here, square root of the average of these values. And that's 0.02. And obviously that gives an idea of how far out our data is in general. And what we're going to do now is try and change this parameter lambda until we get as small a value here as possible. Well, let's just try changing it to 2, and actually the error goes up and it comes down again slightly there, so that's interesting. Let's try and make it 0.5, value comes down, 0.1, value comes down again, so it's clearly fitting a bit better as we make this value smaller and smaller. So let's now see if we can find a way of more efficiently optimizing this value to try and fit this data to the graph. So what I need to do now is to try out lots of different values and see which one produces the smallest value here of the root mean square difference. So again, I'm going to go for a start value of say 0. Let's do a step of 0.01 and a top value of 1. So let's call that lambda start, lambda step, and lambda end, and call this root mean square difference. And what we're going to do now is do some more Visual Basic and step through lots of different values of lambda and see what difference we can make to this root mean square difference. So I'm going to call this the lambda table here, and I'm going to start writing some Visual Basic. So let's call this button search lambda, or call it optimize lambda. And we can start writing some Visual Basic. So for L, I'm going to call, because I need another variable name within the Visual Basic, equals start lambda to end lambda step lambda. Now set lambda in the spreadsheet equals L. Then I'm going to calculate everything in the spreadsheet, and then I'm going to get the output. So root mean square equals, let's look at where my root mean square diff, I call that, equals and then so in lambda table dot offset row is going to be, now I need to get my row out of this, so it is L minus start lambda divided by step lambda. That's what my row is, and column is 0, equals, and that's going to equal lambda, or practically just equal L, because they're the same thing here. Need an extra closed bracket there. Perhaps I need an extra 2 closed brackets, do we? Okay, and the next line I want to actually put in what the root mean square difference is. So the next one is RMS, and then next L, and now I can see what happens when I try running that. Just see if I can fit that out of the way. And so here we go. So L, right, type mismatch. Start on N and see what we've got. Right, because we've called this variable lambda start, this variable lambda step, and this variable lambda end, and we've named them incorrectly there. So that needs to be lambda start. That needs to be lambda end. And that needs to be lambda step. Lambda start. Lambda start. And we'll change these to lambda step. And stop that, and off we go again. So lambda equals L. So you can see immediately that's all changed. Calculate, it's already automatically calculated. Root mean square difference, so that is 2.04 times 10 to the minus 3, which you can see there. And we put the lambda value in here, so our lambda value is 0, and we put the root mean square. We made another mistake there because we put it in the same place, so we need the offset there to be 1. So I have to stop that and try again. There you can see, so this time lambda is 0.01, and you can see the we've got a slightly better fit because we've got 0.00057, and a slightly worse fit, a slightly worse fit again. So I'm going to run that and see where my best fit is now. So if I plot a graph, well, it's pretty clear my best fit is not going to be down that end of the graph. So actually I can probably just draw a graph here and see what's going on. Scatter graph this time. So you can see the low point of the root mean square is here, and that's at 0.01. So we've got an idea that our minimum is somewhere near 0.01. So let's try and refine this slightly. So I make that 0.04 there, and I make this 0.0001. Let's go for it properly, and we can now run that again. And you can see each of these data. Let's just delete that data to keep it clean. And you can see the values coming down of the root mean square difference, so the fit is getting better and better. And if I let that continue, now I can draw a graph of this to see where my minimum is. And I've got a much better idea now. So my minimum is somewhere near here, 0.0098, remarkably close to our original estimate. In fact, we're pretty close to these values here, so I can now refine this again. I can go from 0.009 to 0.01. So 0.009 to 0.01, and in steps of 0.0. .01 in steps 0.0001. Let's delete all that. And see what happens. So this time we started at 0.09. Now you'll notice we need to get a few more decimal points going on here. And let's continue to run that. Well, I've only done 10 there, I need to get an extra 0 in there. Let's do it again. So now we should be getting pretty close to an optimal amount. As you can see, so our best fit here is lambda equals 0.00936. So that's looking pretty good now. Now we can do this in a more sophisticated mathematical way. We can automate some of that process, but that's the essence of fitting a parametric formula to data. And now we've got that where that minimum is. Just look at that again. So we're looking at around 0.00936. Here. You can see that is the minimum data. So 0.00936. And I'm going to put that in there. So that is basically the best fit I can make of the exponential distribution to this data. So let's have a look to see what that actually looks like. I'll just look down the first 100 for the time being. Okay. Well, that's not too bad. We've got a reasonable, we can see in essence what we've done there, but we've got significant problems with it. You might look at that and think, well actually it'd be better if this distribution went like that and went up there. But this is part of the limitations of a single parametric distribution. It's not just trying to fit that part of the graph there, it's also trying to fit this part of the graph here, and that's why it's it's finding a sort of compromise between the two. Now there's different ways we can deal with this. We can deal with a more complicated distribution, such as the log normal or anything with multiple parameters, or we could just splice it. Having sort of looked at this data, we could just say, well, let's make it an exponential distribution from there to there, then do something else with the distribution there. That's a perfectly valid and practical approach. What I'm going to do in this case is, well, first of all, I will actually try and fit just this section of the data. So we'll take out the first 20 pieces of data and see how much better we can do an exponential distribution. But then I'll go on to a 2-parameter distribution as well and look at the more sophisticated convergence techniques. But that'll be in the next video, because I think this video is going to be about 300 megabytes. So I'll stop recording this video and then that can be the next video. Okay.